This video number 4 about the exercises 6.4 and 6.5. Here we see another first order low pass filter, and the exercise required that we derive an expression for the transfer function h of f for the phasor output over the phasor input of the filter shown in figure 610. Show that the h of f takes the same form as the equation 6.9 if we define the breakpoint frequency to be R over 2PL. After this slide, the solution will be shown. Stop or pause the video. Try to solve the exercise yourself first before you see the solution. Before we at all continue investigating the circuit, we have to check if this is really low pass filter. Our memory can play us a trick, so a self-test is a good thing. And the self-test is simply trying to find the 2 points here, the x's on this axis here. Out of the x-axis we have the frequency, up of the y-axis we have V out over V in, so the output, the transfer function output. So we test the circuit by saying, okay, V in now have a frequency of DC. So how would V out become? If we have a DC, so zero frequency here, zero here, actually makes this a very big zero. So this is a short circuit, meaning that V in would actually be V out. So in this case, if V in is 1 volt, V out will also be 1 volt. 1 volt over divided 1 volt, that gives 1 volt. So we are up on the graph here. The x we place here. Then we assume we are at infinite frequency. So V in is 1 volt and infinite frequency. Then, if we have infinite frequency here at this F point, the inductor impedance becomes infinite. And then we don't have any current flow at all through R here. So that means that we actually will see ground through the resistor. So we will see 0 on the output. So we have 0 over 1 volt, that gives us a 0 again. So now we have these 2 points, and then we approximate, okay, the graph will most likely go like this. So this definitely looked like a low pass filter. So now we have got verified our assumption that this is a low pass filter. Then we can continue solving the task. So we have to derive the transfer function. And a transfer function for low pass filter is this one here. We know that. And we get the information that the breakpoint frequency for an inductor and a resistor is R divided 2PF. So how can we now find the transfer function? Well, we start by finding the output voltage, and then we can apply the common method of a voltage divider, because we have an input source and we have output, and we have two impedances. So we can find voltage over the output by simply taking the resistor or the component we're interested in to finding the output voltage over, place on the top here, and then divide by the sum of the component. And here we have the sum, the resistor plus the impedance for the inductor. The transfer function we can see here is the phasor, output phasor over input phasor. We have here the output phasor, we have here the input phasor. So finding the transfer function is simply by dividing by V in on both sides of the equation sign. So we have V out over V in now. So this here is actually the solution, the transfer function, but it doesn't look like this one. So we have to divide by R to get it to look like this one. So we divide every component by R. So R is divided by R, that gives 1. Also R here is divided by R, that gives 1. And then we have to divide this expression with R as well. So we get here. So now we can say, okay, if the breakpoint frequency is R divided by 2PL, we actually can recognize the 2PL here divided by R. We actually can rewrite the equation to be 1F divided by F. So this is the answer for exercise 6.4. Let's continue to the next. Exercise 6.5. Here we have a circuit again, and now we have an input signal that is the sum of components. So the sum of sine waves here with cosinus. We have to find an expression for the output signal V out of time. So how can we verify this circuit? After this slide, the solution will be shown. Stop or pause the video. Try to solve the exercise yourself first before you see the solution. Again, whenever we see a circuit that has one storing element, energy storing element in it, we have to test it. To test if our assumption about the circuit is true. So again, we apply that the input voltage has a frequency of 0, meaning DC level. How would the circuit then behave? If Vin has a DC component, then the capacitor is an open circuit. There will flow no current through it, so I will just have Vin on this pin and on V out as well. So V out is actually equal to Vin. So if my input signal is 1 volt, then I have 1 volt here too. So in this case, I get 1 volt over 1 volt. That gives 1 volt, so I'm up on the axis here. Then the next step is I assume Vin is an infinite frequency, has an infinite frequency. So how will the resistor act? Well, the resistor has no frequency components in it, so it's just a resistor, but the capacitor will act as a short circuit. So at infinite frequency, the capacitor is shorted out, meaning this pin is actually shown to ground. Well, if it's short, then we have 0 volt out. In that case, we're down here at infinite frequency and an output voltage of 0 divided by 1, that gives 0. And then I can approximate, okay, the graph will most likely look like this. So based on my information about the common low pass, high pass, band stop filters, I can say, okay, this is a low pass filter. This is good enough. This is a low pass filter. Then I can use all my tools to low pass filters on solving this assignment. Yeah, let's continue. We are supposed to find an expression for the output signal based on each of these components. So in that case, I need to find the transfer function for each of the components. So let's start. My tools for low pass filter is the magnitude and the phase equation and the breakpoint frequency, how I can find that. And let's calculate it. I have the breakpoint frequency equation here, and then I place the values from the resistor here, and also the value from the capacitor here. You can see it's very convenient to write 500 divided by 2p, because then I just get the value 500 here and they cancel out. 500 times 10 microfarads. That gives me a frequency of 200 hertz. I use this information in my equation, but I need also to find the frequency for the first component, and it's hiding inside here because normally we have 2p times f times t that stands here. So if I can see there's missing a 2, so if I divide 40 by 2 I actually get 20, and that's a hertz in hertz, so I have 20 hertz here. That's the first component frequency. And then I can find the magnitude of the filter and the phase of the filter for 20 hertz. So that's the part of the transfer function. So I apply 20 hertz here as the running frequency, and I have a break as 200 hertz here. That gives me 0.995 times. So this is a factor. And then I have a phase for the first component. The 20 hertz is calculated by help of this. So 20, the running frequency, over the breakpoint frequency, that gives me a phase shift of minus 5.71. So the transfer function for 20 hertz is 0.995 and a minus 5.71 degrees. I'm almost there. Now I just have to calculate the last, if my mouse will work here. So I have now the transfer function. Now I need to, in order to find the V out, I have to take the transfer function times V in. That gives me output. So the V in signal is the amplitude and the phase shift. Here I have 10, but there is no phase indication here, so that gives me a phase shift of 0. So my V in signal becomes 10 and a phase shift of 0. I had previously calculated my transfer function, so now I can see h of f times V in. That becomes the 10 times 0.995. That gives me 9.95 here, and a phase shift of minus 5.71 because I have a phase shift of 0 here. And then I have to turn it into the time domain. So I take my phasor amplitude here and place in front of the cosinus. I know I have 40 pt here, and then I have the phase shift of minus 5.71 comes here. So that's the answer to this part. Now I'm still lagging this and this, but this is solved similarly. The frequency of this one I can find by dividing by 2, because then I need to have 2p, and then I get the frequency times t. So 1000 divided by 2 is actually 500. Then I can find the magnitude and the phase shift in order to later to calculate V out. So the transfer function magnitude is 1 over the square root and 1 plus 500, the running frequency, and the break frequency. That gives me 0.371, a factor. The phase for the second component at 500 Hz is the 500 Hz minus tangents to minus 1, the 500 Hz over the FB. That gives me minus 68.2 degrees. So now I can calculate V out. I have the transfer function. I just need to find V out. This is the amplitude, so that's part of V in. We don't have any phase shift here, so this is becoming 0. So now I can calculate V out as V in, the 5 times the 0.371. That gives me 1.86. And then I have the 0 frequency minus the minus 68.2 frequency. That gives me minus 68.2. So this is my V out frequency. Calculating that into the time domain, we have this voltage here up front of the cosinus, and I have this frequency here, and then I have this phase shift add to it. Then the last component is 5 cosinus 2p 10 to the 4th. So I start by figuring out what is the frequency. I remove 2 times p. Then I have 10 to the 4th as a frequency. That's 10 kilohertz. I add 10 kilohertz into f over fb dB. So I get 0.020 as the magnitude, and the phase for the third component at 10 kilohertz is O minus tangents to minus first 10 over 200 hertz. That gives me minus 88.9 degrees. So now I can calculate V out for the third component here. I take the transfer function at 10 kilohertz and I find out what is V out, V in. That's my phase, the magnitude of the input, and there's 0 phase. So I have 5 minus 0 phase shift. So I can now time my 5 into 0.20. That's actually 0.1 volt. And then the phase shift here is 0. Then I actually get minus 88.9. That means the third component for here, this one, has an output of 0.1 cosinus 2 times 10 to the 4th minus 88.9 degrees. So now I have to turn that into the time domain again. So similar to this one. So how do I get it? I finally turned the output for all these 3 components into the sum of it. So we actually use superposition. We have here the result from the first component, the 20 Hertz, then I have the result from the 500 Hertz, and finally the result for the 10 kilohertz. And this is then the solution for this question. So how can I verify myself that I actually calculated correctly? I can build up the circuit here, and for each component use that it has an amplitude and a phase, and then simulate it. So I put in the amplitude for the 20 Hertz here in. That was 20 Hertz. I had here an amplitude of 10, so I applied that in my simulation. You can see here the source is having an amplitude of 10 and a phase shift of 0, and then I simulate the output. and use the cursors to actually go in and read at 20 Hertz what is the magnitude and what is the phase. In this case, I get a magnitude out of 9.94 and a phase of minus 5.7. That is actually quite close to what we actually have calculated. Here 9.95 and minus 5.71. So check, this is correct. Then I do that also for the 500 Hertz. Remember the source had a 5 as an amplitude. So I go in and check at 500 Hertz what is the output of the filter at 500 Hertz. I go in and read the full line is the magnitude, the dotted line is the phase, and I can see I get 1.85 out, and the dotted is minus 68.21, and that also fits with the output from the filter at 500 Hertz here beautifully. Then the last part was an input voltage of 5 and then 10 kilohertz. So I go in at 10 kilohertz, read that I get 99.97 millivolt and a phase shift of minus 88.8. At this point here, let's go back and see what did we have of 10 kilo. Then the output from the filler would give me 0.1, that's 100 millivolt and minus 88.9. That is actually quite close to my result. So now I have checked that these results are correct with a simulation. And that's how we check ourselves. As engineers, otherwise we may carry an error out to our customers, and that could become expensive. So end of video 4. Thank you for watching.